The user's view of memory is not the same as the actual physical memory. Users prefer to view memory as a collection of variable-sized segments, not a linear array of bytes. There is no order among the segments. So, a segment is a logical unit such as main program, procedure, function, method, object, local variables, global variables, common block, stack, symbol table, arrays. So like this picture. This is the user's view of a program. We look at our source program as main program, symbol table, and the system function, and the stack, and the subroutines like this. And there is no order among these segments. Okay, this is our view of a program. Each of these segments is of variable lines. The lines is intrinsically defined by the purpose of the segment in the program. Elements within segment are identified by their offset from the beginning of the segment. So this is segmentation. So segmentation is a memory management scheme that supports this programmer view of memory. A logical addressing space is a collection of segments. Okay? Each segment has a name and a length. The addresses specify both the segment name and the offset within the segment. Okay, so if the system uses segmentation memory management scheme, then the logical space is a collection of segments, and the logical address consists of two tuples. The first part is the segment number, and the second part is offset. I emphasize that in segmentation, the logical address is consists of two parts: segment number and the offset. For simplicity of implementation, segments are numbered and are referred to by a segment number rather than by a segment name. So look at this picture. Okay, this is the logical address space for one process. This is the physical memory, and we see they have 1, 2, 3, 4, 5, altogether 5 logical segments. And each segment is put into the physical memory. And you can see the whole process is not contiguous. It is non-contiguous in the main memory. Okay, separated in the main memory. And this is the segment table. And in this table, we have the base address for the logical segment 0 and the size for this segment. So here, segment 0. And the logical segment 1, the base is this one, 6300, so here, and the length is 400. And as for logical segment 2, the base address is 4300, this one, and the size is also 400. So this is the segment table. Okay, and when user program is compiled, the compiler automatically constructs segments reflecting the input program. A C compiler might create separate segments for the following: the code segment, the global variables, the heap from which memory is allocated, stack, the procedure called stack, to store parameters and return addresses, and the standard library. Libraries are linked in during compile time might be assigned separate segments. The loader would take all its segments and assign them segment numbers. Okay. Segmentation hardware. Although the programmer cannot refer to objects in the program by a two-dimensional address, the actual physical memory is still, of course, a one-dimensional sequence of bytes. Thus, we must define an implementation to map two-dimensional user-defined addresses into one-dimensional physical address. This mapping is effected by the segment table. Okay, we already see each process has a segment table. In this table, each table entry has the base address. Here, just now we already see it, the base address. And the limit, also we can say the size for this segment. Okay. The segment number is in the logical address is used as an index into the segment table. Segment table base register points to the segment table's location in memory. That means you must remember each process has one unique segment table. And this segment table is also stored in main memory. So segment table base register, this special register, points to the segment table's location in memory. And the second special register, this one, segment table lines register, indicates number of segments used by a process. Okay. And memory protection, such as logical address, consists of two tuples because logical address consists of two tuples. The first part is the logical segment number, and the second part is the offset within the segment. So the hardware, the segmentation hardware, use this segment number compiled with first use this segment number compiled with this register, segment table lines register. If it is larger than this register, then the hardware will trap to the operating system. It is addressing error. The logical address is illegal. If the logical segment number is smaller than this segment table lines register, it is legal. Then the hardware will use the offset. We will use the segment logical segment number as an index to search the segment table and get the limit of this logical segment and compare the offset with the limit. If it is smaller than the limit, then it is legal. Otherwise, the hardware will trap to the system, okay, to the operating system, and the this address is illegal. And if the address is legal, is valid, then the hardware will use the base address plus the offsite and get the one-dimensional physical memory address and assigns the memory, fetch the data or instruction. Okay. So let's look at this exercise. One precise segment table is like the above slide. Okay. Please translate the following logical address into physical address. First, the logical address is two-dimensional. The logical segment number is 1 and the offsite is 300, so we use it to search this table. 1, okay, and we'll find the limit is 400, and now the offsite is 300, so it is legal. It is legal. So we use the base address 6300 plus the offsite 300. We get we use the base address 6300 plus the offsite, we get 6600. So this is the answer for the first one. And the second segment number is 2 and the offsite is 600, so we search the table here. The limit is 400 and the offsite is 600, so this address is illegal because it is larger than the limit, this limit, so it is illegal. So the second address is illegal because this one is illegal because the offsite is larger than the limit, and this one 3700. We look at it. The segment number is 3 and the limit is 1100 and the offsite is 700, so it is smaller than the limit, so it is legal. So we use the base 3200. We use 3200 plus the offsite, and we get the physical address. This is the physical address for this logical address. Okay. Segmentation advantages. First, protection. With each entry in segment table, we can associate by placing an array in its own segment. The memory management hardware will automatically check that array indexes are legal. Sharing of code and data. Each process has its own segment table. Entries in two different segment tables point to the same physical location. Segments are shared. Of course, only read-only segments can be shared. Look at this picture. We have two processes, and the For first precise, the logical segment 0 is editor, and the segment 1 is data. And we can see in this segment table for precise P1, the first segment is the limit and the base, so this one. And for precise P2, this is the logical memory space. And also, the first logical segment is editor. The second logical segment is for data. And we can see in the segment table for precise P2, we have the same base address and the same limit address. So in physical memory, only one editor, one copy of the editor, and two different data segments. So we implement sharing, okay, segment sharing. And comparing with page sharing, it's easier. Okay, so of course only read-only segments can be shared. Okay. Allocation. The segments are of variable lengths. Memory allocation is dynamic storage allocation problem. For each segment, each logical segment, the operating system must allocate contiguous space for each logical segment. So, and because each segment has different lines, so it is dynamic storage allocation problem. We can use the algorithm first fit, best fit. And because we use dynamic allocation scheme, so there are external fragmentation, no internal fragmentation.